it is known to us, if div of a vector is equal to 0, then that vector should be expressed in terms of curl of another one vector. In the present case, the div of magnetic induction is equal to 0. This condition is called solenoidal. Immediately, it leads to the condition of B equal to curl A. Here A is called vector potential. Suppose curl E equal to 0 is taken for our consideration. Curl E equal to 0. This condition is called irrotational, because in order to study the rotation motion of fluid, we are taking curl. If the curl of a vector is equal to 0, then that condition is called irrotational. Most probably, the curl operator is called as a rot, since it is used to study the rotational motion of fluids. But here div B equal to 0 is our solenoidal condition. Now, the term A is called vector potential. In electrodynamics, we can introduce the term vector potential A such that the vector potential leads to the magnetic induction B to satisfy the solenoidal condition div B equal to 0. Now we have to derive an expression for the vector potential A using our Biot-Savart's law. According to Biot-Savart's law, magnetic induction at a point due to the current element dl is mu naught I divided by 4 pi dl vector cross r vector divided by r cube. But gradient of 1 by r equal to minus of vector r divided by r cube. Here is a proof for that. Vector r is equal to I into x plus j into y plus k into z. Modulus of vector r equal to x square plus y square plus z square power half. Gradient of 1 by r equal to, this is the gradient operator and is allowed to operate on the function 1 divided by x square plus y square plus z square power half. Now bring this term to the numerator, then power half is changed into minus half. Now allow the gradient operator to operate on the terms. After simplification, you can get this result. I into x plus j into y plus k into z with a negative sign. This is our r vector, minus of r vector. This is our r cube, since the value of r is x square plus y square plus z square power 1 by 2. You know that gradient of a scalar is a vector. So finally we have arrived a vector. Now come to this equation. In equation 1, the term r vector r divided by r cube should be replaced by minus of gradient of 1 by r. See here, this vector r divided by r cube is replaced with negative sign of gradient of 1 by r. To convert this negative sign into positive, interchange these two terms. dl vector cross grade of 1 by r is rewritten as grade of 1 by r cross dl vector. Now the negative sign is changed into positive. Now we have to evaluate the value of grade of 1 by r cross dl vector. For that, use this vector identity. Curl of pi a equal to grade pi cross a plus pi into curl a. Now del cross dl vector by r equal to grade of 1 by r cross dl vector plus 1 by r to curl dl vector. Now we need this value, therefore bring this term to the left hand side. So grade of 1 by r cross dl vector equal to curl of dl vector by r minus 1 by r, then curl of dl vector. See here, instead of this we have to substitute this one. In our case 1 by r is pi, dl vector is a vector. Now we have arrived at the equation 4. We know that the current element is not a function of the coordinates x, y and z. Therefore, curl of dl vector is equal to 0. Now the equation 4 takes the new form of equation 5. The total magnetic induction at a point due to the closed current loop is, just we have to integrate equation 5, then we can get this form. If div b equal to 0, then b equal to curl A. Now compare the equation 6 and 7, we can get the value of A. If you remove the term del cross, the rest of the terms represent the vector potential. Mu naught I divided by 4 pi integral dl vector by r is our vector potential. If the region under consideration is specified by current density J, then I dl vector is replaced by current density J into dV. So the equation 8 is presented in the form of equation 9. If rho be the current density per unit volume, that is rho equal to J divided by V, then J equal to rho into V. Now the vector potential is taking the new form of equation 10. Just instead of J, we have written rho into V. According to Ampere's circuit law, integral b dot dl is equal to mu naught into I, but I equal to integral j dot ds. According to Stokes theorem, b dot dl equal to curl b dot ds. Stokes theorem converts the line integral into surface integral. From the equations 11 and 12, we may write curl b dot ds equal to mu naught into integral j dot ds. So curl b equal to mu naught into j. But b is our curl A. Del cross A equal to mu naught into j. Now use the identity. Del cross curl A equal to grade of div A minus del square A, which is equal to, right hand side is mu naught into j. If div A equal to 0, then del square A equal to minus mu naught into j. The equation 15 is known as Poisson's equation for vector potential. You know the Poisson's equation in terms of scalar potential. For that, consider the Gauss law in electrostatics, that is E dot ds equal to q by epsilon naught. Now we have to change this in terms of volume integral using our Gauss divergence theorem. Del dot E dV. Yes, we have converted this surface integral into volume integral, which is equal to 1 by epsilon naught integral rho dV. This q is replaced by integral rho dV. Now div minus rho by epsilon naught entire is multiplied by dv equal to 0. Here dv not equal to 0. Therefore, dou V minus rho by epsilon naught equal to 0. This leads to the condition of dou V equal to rho by epsilon naught. We know that E equal to gradient of scalar potential with a negative sign, E equal to minus grade pi. Now del dot del pi, which is equal to minus rho by epsilon naught, del square pi equal to minus rho by epsilon naught. This is our Poisson's equation in terms of scalar potential pi. This is our Poisson's equation in terms of scalar potential pi. This is a Poisson's equation in terms of vector potential A.